Okay, so last time, the last thing we did was we computed the degree of the polynomial map when you restrict it to a circle. In fact, what we did, the last thing we did is we had an example, which was the polynomial z to the n, where, well, I actually allowed n to be negative, where f is a map from S1 to S1. And I showed that the degree of f is equal to n. Okay. Well, we can generalize this to a very simple situation, which is if you look at a map that goes from the boundary of the two ball of radius r to, say, S1, which just takes Zn over the norm of Z over R to the n. Okay, so this is diffeomorphic to an S1. This is based very similar function, and it's pretty clear that this function also has degree n. Okay. Or if you wanted, you could just take this to have values on the circle of radius r to the n. Sorry, no, that's right. Yeah. Okay. So now we're going to use this example to prove a very beautiful and well-known theorem, which is the fundamental theorem of algebra. Fundamental theorem of algebra. What does it say? It says if you take a complex polynomial, the polynomial of degree n, then and the positive degree, so not 0 degree, then P has a root. That just means, i.e., there exists Z and C such that P of Z equals 0. Okay? So how do we prove that? It's kind of amazing that, this is the fundamental theorem of algebra, and is used in algebra all the time. But to prove it, we actually need topology. So there are a lot of different proofs, but I think most of them use the topology of C in some way. And this proof is going to use degree theory. So let's write the polynomial like this. So P of Z is Z to the n plus a n minus 1, Z to the n minus 1, etc. plus a0. I mean, I'm just going to assume that coefficient in front of Zn is 1, but it's clearly, if it's true for polynomials of this form, it's clearly true for all polynomials, because you can just divide by the leading term. Okay, so now I'm going to fix some r, some real number, large positive number, such that r to the n is greater than the absolute value of an minus 1, r to the n minus 1, plus, etc., plus the absolute value of a0. Okay, so I just want to fix r sufficiently large. And you can always do that, because when you look at this divided by that, this goes to infinity as r goes to infinity. The ratio of the left side, the left-hand side by the right-hand side. So we can always get this to be greater than 1 for r sufficiently large. Okay? And why do I want that? Because now I want a homotopy from this polynomial to the polynomial z to the n, but just restricted to, so let me write, now I'm going to write pt of z to be, this is a polynomial with a parameter t, and this is just z to the n plus t times the rest of the polynomial. So a to the n minus 1, z to the n minus 1, plus etc., plus a0. So this is, I'm going to define this for t between 0 and 1. Okay? And what is clear is that P0 is just the polynomial z to the n, and P1 is just P. Okay. And now, note that if the norm of z is equal to r, then the absolute value of pt of z, or the norm of pt of z, this is going to be greater than, I'm going to use the triangular inequality, the norm of z to the n minus the norm of an minus 1, norm of z to the n minus 1, minus etc. minus a0. Okay? And this is equal to Rn minus an minus 1, Rdn minus 1, plus etc. plus the absolute value of a0. And we suppose that R is big enough so that this is bigger than 0. So this means that the polynomial pt, sorry, this is for, so at first you have a t here, but you can get rid of the t. So yeah, let me, let's, so first you have a t that multiplies this, but t is less than or equal to 1, so this is going to be bigger than or equal to z to the n minus an minus 1, norm of z to the n minus 1, etc., norm of a0, and now this is bigger than a 0, yeah, because the norm of z is r. So this is r to the n minus a to the n minus 1, r to the n minus 1, plus etc. plus norm of a0. And this is bigger than 0 because this is equal here. And this is bigger than 0 because we assume that r was large enough. We assume this equation here. Okay? This implies that pt of z is always different from 0. So this is for every z in the boundary of this ball. So this is in the points of norm r, and t between 0 and 1. Hence, P0, when you restrict it to this to the circle, is homotopic to P1 when you restrict it to the circle. Then the degree of P is equal to, sorry. Now you can divide it by the norm. So then yeah, so then this is also true when you divide them by, right, it's obvious they're homotopic, but the point is that even when you divide by the norm, they're still homotopic because the homotopy never hits 0. So they have the same degree. So the degree of P over norm of P is equal to the degree of Zn over R to the n. And by the example of last time, this generalization, this degree is equal to n. Okay? So now, And remember that the degree is just the intersection yeah, it's just the intersection of this function with some regular value. Okay. And now I can recall the proposition from last time, which is that, well, this guy here is defined on a ball on a circle of radius r. So this is the boundary of the disk of radius r. So if P does not have a zero, if P doesn't have a root in this ball of radius r, then this function P over norm of P extends over the whole ball. Then P over norm of P extends over this whole ball. And so we proved last time, either directly for the degree, or you can use, the slightly more general theorem for the intersection number that if a function extends over some compact manifold whose boundary is that, then the degree has to be 0. Or this intersection number has to be 0. Okay, and that's a contradiction. So that implies that P has to have a root inside this ball. Okay? All right, any questions about this? Maybe you've seen this theorem before. You've probably seen the theorem, and you've probably seen a proof of that's similar to this. You can do that with integration too, kind of something similar with the Ram cohomology. But anyway, I think this is a nice little application of degree theory. Any questions? So one thing that's behind this is the idea of a winding number. So let's talk about winding numbers now. Winding numbers. And then a nice application of it will be the Jordan-Brouwer separation theorem.
Professor.
Oi.
O exemplo do círculo, o exemplo polinomial que você deu primeiro.
Sim.
Ele é um recobrimento, certo?
Sim.
Isso funciona em geral para recobrimento? O grau a cardinalidade da fibra?
Depende, você tem que ver se o mapa ele é orientado ou não, né? Se ele está preservando a orientação ou não.
Sim, certo.
O grau módulo 2 é o número... se você contar o número de pré-imagem da fibra, porque o recobrimento, todos os pontos na base vão ser pontos regulares, vão ser valores regulares, né? Então você simplesmente pode contar, mas tem que ter só essa questão de olhar para a orientação para saber o grau de verdade.
Mas no caso vai ser sempre mais ou menos então essa quantidade? Porque o recobrimento...
se o mapa em cima for conexo, sim.
Sim. Se
a variedade em cima for conexa, sim.
Ok.
Então basicamente eu acredito que na maioria dos casos interessantes a resposta é sim. O grau do recobrimento é simplesmente o número de... o grau do recobrimento é o grau do mapa. Okay, so let's talk about winding number, which is basically a generalization of this idea. So let X be a compact and connected manifold without boundary. And then now you can talk about the winding number mod 2, or you can talk about the oriented winding number. So sometimes if you want the numbers in Z, so I'm going to do both at the same time. If we want a number in Z, we need to require orientability. If we don't require orientability, we can still get a winding number in Z mod 2. Okay. And let's say the dimension of X is n. And let f be a function from x to r n plus 1, which is smooth. And let z be a point which is not in the image of f, such that the image of f, such that z is not in the image of f. So now we can define the winding number of f relative to z. So now we define the winding number like this. So we can let uz be a function from x to Sn, defined by, so uz of x is the f of x minus z divided by f of x minus z norm. Okay, so this, because f of x is never equal to z, then this denominator here is never 0. So this is well defined. So now we can define the winding number of f with respect to z to be the degree of this map, uz. And again, you can do over z if x is oriented, or you can do it over z2 if x is not oriented. Okay, so this is over z if x is oriented, or over z2 if x is not oriented. So again, if x is oriented, then we can look at the pre-images and they come with signs, and we can just sum all the signs, and you get an integer. But if it's not oriented, you still have transversality. You can still pick the pre-image of a regular value that will give you a finite set of points, and then you can just count them, and this number will behave well with respect to homotopy mod 2. Okay, so observation is that if ft is a homotopy of maps, that never hit z, then the winding number is preserved. Then the winding number of ft z is constant. Mt. Okay, so let's just look at some examples. I think that's kind of nice. Well, the first one say that. Well, I think the most common example is like, think of a curve. Think of your f to be a map from S1 to R2. That doesn't hit. No, let's say a map from S1 to R2. So some curve. So I don't know. Okay, and let's say I have. And let's say this is oriented. So I'm orienting my S1, so I actually have oriented winding numbers. So let's say I have a point P, a point Q, a point R, and a point S. So I have different points in R2. And first thing we can see is what is the winding number of F with respect to P. So what we can do is we can look at this curve, and because this winding number is invariant under homotopies that never hit Z, and maybe I should say why. I'll just say in a few words. I won't write it down. It is invariant because if you have a homotopy of maps F that never hit Z, then you get an induced homotopy of these maps UZ. You just put Ft here, and this will always be well defined. So you will have a homotopy of maps from X to Sn, so they have to have the same degree. Okay, so how do you compute, for example, the winding number of F with respect to P? Well, you look at this curve, and you can actually you can deform this curve to a curve that just goes around P twice, like this. And then now, if you know, it's kind of easy to see when you write it like this that the U that you obtain is basically the same as Z squared divided by norm of Z squared, or something like that. Okay, so for each any point will be a regular any point on the target will be a regular value, and then you reach it twice, and it's positively oriented. Okay, so the winding number of P is going to be equal to 2. And then the winding number of F with respect to Q, well, now we can actually homotope this guy to, let me do this. This is the one going twice. Now here you can actually homotope this path to a map that just goes around once. You can see that. So the winding number of F with respect to Q is going to be 1. And then with R, the winding number of F with respect to R, now I can homotope this to a map that goes around R, but that rotates in the other direction. So this is going to be -1. And the winding number of F with respect to S, well, we can homotope this to a map that is just constant without intersecting S. So this winding number is going to be 0. Okay? But the cool thing is you can actually don't have to do, maybe you've all seen this for S1 in some way or another. Maybe this is taught often in complex analysis. You can integrate the function 1 over Z or something. And then you get, multiples of 2 pi I. But, so it's going to be the same actually. But the cool thing is that you can do this in every dimension, and the domain only has to be compact and connected. And the dimension of the domain has to be 1 less than the dimension of R, of the Euclidean space. Okay. So one example, another example, this just kind of like this, but it follows from the previous proof, is that if you take a polynomial, then the winding number of the polynomial restricted to a circle of large radius relative to 0 is equal polynomial of degree n. This winding number is going to be equal to n. Okay, that's just because this is exactly this is just by definition the degree of P over P. Okay. So now maybe I will state a proposition which is actually very nice and useful. Before I say the proposition, any questions about these examples?
I have a question.
Yes.
What if you accidentally have a 0 on the boundary, or if a function is surjective, you couldn't define?
No, then you don't define it. Yeah, the function can't be surjective because of Sard's theorem.
Right.
Yeah, a smooth function from an n-dimensional manifold to Rn plus 1 cannot be surjective. Yeah.
Right.
Yeah.
Okay.
But you cannot yeah, then you can't define the winding number. Like if you have a point on the image, then the winding number is not defined.
So if you already had a 0 in the polynomial, you forget your problem, man.
Yeah, so this is only for R sufficiently large. Because I proved, if R is sufficiently large, then the polynomial does not have a 0 along that circle.
All right, perfect.
Yeah. Okay, so this proposition actually will say in particular that the polynomial, because the winding number is n, then the polynomial will have n zeros inside of this ball. This proposition actually applies more generally. So suppose that X is the boundary of some compact manifold. So D is a compact manifold. And suppose that your function f extends to a function capital F from D to Rn plus 1. Then the winding number, and now we can choose some yeah, so, and we can assume without loss of generality that F is transverse to Z. Okay, this is because of the same corollary that I used a couple of times last time. Because we know that Z is not in the image of F, so F is transverse to Z. So we can actually, if you can extend it, then you can perturb your function away from the boundary so that it's actually transverse to Z. So the claim of the proposition is that the winding number of F with respect to Z is equal to the number of points in the pre-image of Z. And here you can look at this equality in this number. Let me this number and this equality. Then again, you have to look at two cases: when X is oriented and when X is not oriented. So when X is not oriented, this equality is mod 2. Okay, so this is an equality in Z mod 2, or maybe I should say in is in Z2. And if X is oriented, then this number is a signed number. Okay, so I'm not just counting all the points, but I'm counting all the points with signs. So some points count positively and other points count negatively. Okay. And the proof is basically the same. So I'm not going to do two proofs, but I'll just point out where the signs come. Okay, any questions about this proposition?
I have a question about what you said before.
Mm-hmm.
Why does Sard's theorem imply that the map is not surjective? Because Sard only says that the critical points have measures 0, right?
Yes. But everything in the image, the critical values have measure 0, but everything in the image is a critical value. Because of the dimension.
Okay.
Yeah. So it can only be a regular value if you're not in the image of a map from an n-dimensional manifold to an n+1 dimensional manifold.
Okay. Yeah. I got it. Thank you.
Okay, great. All right. So is the proof clear? I mean, the examples that I showed before, you can kind of see that, when you had that map from before the proof. Let's just go back to the examples. So I don't know, I had something that, I don't know, it was more complicated. But, I don't know, something like this. But if I took this point here, what I can do is when I write this picture here, I can actually extend this map from a map of S1 to R to actually a map of the disk, of the 2 disk to R2. But the point is that this map is now going to actually have to hit this point here twice if it's transverse. There, so you can kind of see, how do you even do that? Like you kind of unfold it, and it's not hard to see. You can define at least a continuous map, and then you perturb it, and it's smooth. Okay, and the same for the other points. I had put a point here, I put a point here, and I put a point here. Okay, so let's prove the proposition. So in the first case, let's suppose if z is not in the image, so let me remind you of the setup. So I had my function f, which was defined on the boundary of D, and then I've extended it to all of f, to all of D. And then I want to look at the pre-images of z, and I know they're all in the interior of D, and I want to count them, and I claim that that's equal to the winding number. Okay, so the first, the trivial case is when z is not in the image of capital F. So maybe, like for example here, if my z is this point here, I can extend my function to the whole disk, and it still never hits z. Okay, so if z is not in the image, then we know that the number of pre-images is 0. Moreover, we can extend the map uz to a map on all of D. You can just use the same definition, basically you can write U, capital uz of x is capital F of x minus z over the norm of capital F of x minus z. Okay, and then basically using the same proof as before, the number of the degree of this map, because it can be extended to a compact manifold with boundary, it has to be 0. So the degree of this map restricted to D, which is the same as uz, has to be 0. So in the case that z is not in the image, we kind of get it's a trivial, it's pretty trivial that they coincide. And this, by definition, is the winding number of F relative to Z. Okay, so now let's suppose that this is not empty. So if it's not empty because the domain is compact, then now suppose then the pre-image is going to be a finite set of points.
Professor,
Yes?
posso fazer uma pergunta? A gente tem que assumir, no caso orientável, que D é orientável também? Orientável.
Sim.
Tá.
É. Aham. No caso orientável, você tem que... Não. Senão, você só consegue uma igualdade módulo 2. Né? É, porque uma variedade orientável pode ser o bordo de uma superfície não orientável. Eu acho que se vocês quiserem, se você quiser brincar com isso, de repente você consegue algum exemplo interessante. Sei lá, com a faixa de Möbius. Deixa eu pensar. Se você projetar a faixa de Möbius para R2, de repente você consegue olhar para o bordo como uma curva, e aí você olha para o winding number de algum ponto, e isso aí, quando você olha para a faixa de Möbius, não vai corresponder ao número de interseções, o número de imagens. Eu acho que é até um exemplo interessante. Bom, mas vou deixar você pensar sobre isso, qualquer coisa você me pergunta depois. Okay, so, de nada. So the preimage of Z will be a finite set of points, and by the inverse function theorem, capital F is a local diffeomorphism near each xi. So we can actually find, basically we can say that near each I, we can find charts around xi and around z, so that F is the identity. But because I'm actually worried about orientation a little bit, I want to only look at charts that preserve orientation. So we can find orientation preserving charts phi I from a neighborhood of xi to r n plus 1 and psi from v to r n plus 1. So these are charts around xi and z for every I, such that when I compose F with the preimage of psi, when I look at F in charts, this is plus or minus the identity. So I'm going to write the sign as, I'm going to write sigma of I times the identity, where sigma of I is plus or minus 1. Okay, so this sigma of I is really going to be, it's the same as the sign of this point, the same as the sign of xi. So it's whether the derivative of F preserves orientation or reverses orientation. Okay, so now what we're still looking at the winding number. So what we want to do is we want to concentrate, look at, prove that the winding number of the whole surface, hypersurface, this boundary is the same as the winding number concentrated around each of these pre-images. So let me draw a picture. So if you have, I don't know, something like this, this is the image, and then when I look at the domain, I have something like this. What I want to prove is that the winding number somehow I can concentrate on these guys. So, this corresponds to a curve here and the same curve here. Okay, so how do I do that? Well, it's actually pretty simple. I just have to look at a small ball around each one of the xi's. So I can let epsilon be a small number such that the ball of radius epsilon is contained in the image of all the charts for every I. So now I can look at the pre-image of this ball. And actually, I'm going to look at the following manifold. I'm going to look at D minus all of these guys. Minus the union, the disjoint union of these balls. So here you should see D as being W as being this region. This technique that I'm doing, maybe it's very classical in complex analysis. So I'm sure all of you have seen it at least on the plane, but you can do this in any dimension. If you define winding numbers, degrees, and all of that, you don't need to just integrate 1 over z, or 1 over z minus a point. So now, what can we say here? We can say that by the construction that we had before, the degree, of now this. So if you want I can look at the intersection number of my function u. Yeah, so sorry, let me say one more thing. So in W, so we can extend uz to W because because the function f of capital F never hits z in W. So since W doesn't intersect the image of capital F, is equal to the empty set. Since okay, so you can just define in this set, you can just define the same thing. So you can just define uz to be uz of x. This is exactly what I did in the other case. It's f of x minus z over the norm of f of x minus z. So because of this, now I can actually say, the intersection number of u on the boundary of W, of uz, on the boundary of W with z has to be equal to 0. Okay, this is because uz extends to a compact manifold. And then now I can write this as a sum. So I can write this as the sum, well, I'll write it like this. So the boundary has the component of the boundary of D, and then it has the boundary of all these guys. But these guys the boundary comes with the opposite orientation. So this is the intersection of U on the boundary of D with Z minus the sum of the intersection of U restricted to this guy. So restricted to, sorry, this is UZ. UZ. Restricted to the boundary to phi inverse of the boundary of Bn plus 1 epsilon from I equals 1 to k. And then by definition, this is just the degree of the function f. So this implies a degree, this is just the degree of this UZ, and this is just the degree of this guy. So this is the winding number. So this implies that the winding number of the function f restricted to dz relative to z is the sum of the winding numbers of f restricted to this guy here, so restricted to phi inverse of b n plus blah 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 of epsilon relative to the point C. Okay, so this is kind of the argument that I was saying. You replace the winding number of the whole thing by a sum of local winding numbers. And what's the advantage of that? Well, the advantage of that is that now these are very easy to compute because I know exactly what f is like. So if I call, maybe I can call fi, this function f restricted to this ball. One, two, three, yeah. So what we have is that the winding number that we want to compute equal to the sum of the winding numbers of fi relative to z. I equals 1 to k. Okay, so now I can actually use the charts, and because I have orientation preserving diffeomorphisms, everything is going to be preserved. The degree is going to be preserved, so I can compute this winding number. The winding number of fi relative to z is going to be equal to the winding number of psi composed with fi composed with phi inverse of 0. Okay? And the point is that this guy is just plus or minus identity. So this is just the winding number of sigma of I times the identity. And this is easy to compute. You just look at a map from the Sn to Sn, and this is just going to be the number sigma of I. So plus or minus 1. Okay? And also, moreover, the number of pre-images of Z, that's actually just the sum of sigma I. Because I told you, so for each xi comes with a sign if it's oriented. If it's not oriented, it's just this number. And everything, plus or minus 1 is the same. But if it's oriented, then we have this plus or minus 1. And you just count the number of pre-images, but you count them with a plus if the function preserves orientation. If df preserves orientation, you count with a minus if it doesn't. Okay? So now we're basically done. So this this sigma I, this sign, is the same as the winding number of fi, and the sum of the winding numbers of fi is the winding number of f relative to z. So this is now equal, if you combine all the equations here, this is the winding number of f relative to z. Okay. I could, maybe you could write, to make the notation slightly simpler, you could write this f intersection of f relative with z, but we haven't quite defined the intersection number when the manifold has boundary, and that's because the invariance is a little tricky. It's not. You have to see, it's a little bit of a tricky statement. But anyway, this is what it would be. Okay, so anyway, this is the end of the proof of this proposition. So in other words, you can compute the winding number by extending the function to a compact manifold that bounds the original manifold, and counting the number of pre-images. That's the moral of the story. Any questions? No?
The winding number is the
Yeah?
same in local coordinates because
Yes.
the charts are orientation preserving.
Yes, if it has to be, it's the winding number, the degree. It's because the degree is well defined. If you take a diffeomorphism that's orientation preserving, the degree will be preserved.
Okay.
That's because if it's a diffeomorphism, then the degree is just that you count the number of pre-images of a regular value. So under diffeomorphism on the manifold, on the domain and target, regular values are taken to regular values. And the number of pre-images is going to be the same. And if the diffeomorphisms are orientation preserving, then the signs are going to be the same as well.
Okay, so the degree is the same.
Yeah, the degree is the same, and therefore the winding number is the same. Yeah. Okay. Gilliland-Pollack, if you want, it breaks this proof down into more steps. You can redo it if you want in another way. Other questions?
Eu fiquei um pouco perdido. Você pode voltar uma página, por favor? Nesse lado esquerdo, eu não entendi por que o I de o Z restrito ao bordo de W é o I menos essa soma de 1 até K, aquele lado direito.
Porque o bordo de W é o bordo de D, união com esse bordo daqui, com a orientação contrária.
Ah, sim. Tá bom. Obrigado.
Tá? De nada. Mas você entendeu por que esse I é 0? Desculpa, quem que tá falando?
Eu, Luciano.
Ah, Luciano. Você entendeu por que isso aqui é 0?
Ah, não, isso sim.
Ah, tá. Beleza.
Entendi.
Bom, beleza, então. Mais alguma dúvida? Então, vamos voltar no exemplo do polinômio. Okay, let's go back to the example of the polynomial. So our polynomial, we take a polynomial of degree n, and we know that, so since the winding number of P restricted to some circle of large radius, this is n, or r sufficiently large, then this implies that, when you extend this function to the whole ball, for example, by the polynomial, then P has n zeros, including multiplicity. What does that mean? So, maybe 0 will not be a regular value of P. So if 0 is a regular value of the polynomial P, that means that all the zeros are single zeros. So the derivative is injective, so all the zeros are isolated. But sometimes, as you know, you have double zeros and stuff, and that means that 0 is not a regular value. And how would you make sense of that? You'd say, well, the number of preimages of 0 could be smaller than 0, but some of them come with multiplicity, which means that if you perturb either the polynomial a little bit or 0 a little bit, you're going to have as many zeros as the multiplicity at that point. Okay, so the idea is, like, say you have the simplest polynomial P of z, which is e to the n. Then this example, where I'm claiming that, actually in this case, for any radius positive, any positive radius, you have exactly n zeros. But you're like, well, there's only one number that is a 0, which is the number 0. But that's because, in this case, 0 is not a regular value. So what does it mean? How do you count the number of zeros? You actually have to perturb a little bit. So when you perturb your polynomial a little bit, say minus epsilon, now you're going to have n roots. Okay, so that's what it means for 0 to have multiplicity n. Okay, any questions about this?
Eu não entendi direito. O que você está dizendo é que se você tiver um polinômio que tem um zero, que tem multiplicidade, você pode perturbar ele para ele não ter multiplicidade mais.
Exatamente.
Ah, tá.
Na verdade, para ele não ter multiplicidade, não. Ele vai gerar mais do que um zero.
Uhum.
Uma das formas de você ver isso, né, é você usar esse winding number, porque se você pegar um zero do polinômio e você pegar uma curva em volta dele, que só está em volta desse zero, né, o winding number do polinômio em relação a esse ponto vai ser exatamente, ao longo dessa curva, vai ser exatamente a multiplicidade daquele zero. Maybe this is an exercise that kind of joins a little bit of algebra and topology. So this is another example, or exercise maybe. Exercise is if you take a polynomial, and you take z a zero of the polynomial. And then you can let gamma be a curve that goes around an injective curve that goes around z once. So I mean, you could write this explicitly. Gamma of t is z plus epsilon times e to the it. And you want to make sure, this is an isolated zero. So z, I mean, all the zeros of polynomials are isolated. But so you want this curve not to bound any other zeros. So, kind of, I'm not going to write this down. So, just going around z, bounding only c as a zero. Okay. Then the multiplicity of z is equal to the winding number of gamma with respect to z. And this will imply that if you do if you perturb your polynomial, then you're going to have as many zeros as this multiplicity or the winding number. Okay, as long as now 0 is regular. But as you know, most perturbations, a generic perturbation will for a generic perturbation, all zeros will be single zeros. You won't have multiplicities.
Acho que você quer dizer P composto com gama.
Oi?
Winding number, não tem que ter o P ali?
Sorry. The winding number of P restricted to gamma of S1. Yeah. The winding number of gamma with respect to Z is going to be 1. It's just a curve that goes around Z. Yeah. Thank you. Okay. Any other questions? Well, so now we can talk about the Jordan-Brouwer separation theorem, which is a nice application of winding numbers. So this is the Jordan-Brouwer separation theorem. You might have seen the Jordan curve theorem, separation theorem, and this is the generalization of this theorem to higher dimensions. But in particular, one of the cases is the case for curves. So it says the following: let X in Rn be a compact connected hypersurface. So it just means a submanifold of codimension 1. So this just means that the codimension is equal to 1. That's what it means to be a hypersurface. Then the complement of X is the disjoint union of two open sets where U1 and U2 are open sets such that U1 bar and U2 bar are submanifolds, are manifolds with boundary with boundary X, and U1 is bounded and U2 is unbounded. So that's the statement of the theorem. So if n equals 2, this is just saying if you take a simple closed curve, so some curve doesn't intersect itself. I mean, the point is that it could be very complicated. Then the complement of that, there is an inside and there's an outside. That's kind of the point. So you have a U1, which is the inside of the curve, and you have a U2, which is an outside. Okay? Well, let me actually call, it'll be clear later, maybe I'll just call U1 and U0. U0 is going to be unbounded and U1 is going to be bounded. Okay, so let's prove this. The proof is actually not very hard, but it's still very interesting, I think. It really, you can see the power of this winding number technique. So let's split it in a few steps. So the first step is to show that the complement of X has at most 2 connected components. Okay, so let's fix a point, a little x in X, and an open neighborhood of X. So you can think of an open neighborhood of X. So this will be diffeomorphic to something like this, like a little ball, little b n minus 1 of epsilon times minus epsilon epsilon. So, you know. And b n minus 1 epsilon times 0 is what's contained in X. Okay. So I can't write very well. So what I'm going to do is I'm going to say without ever crossing X. So how do we do that? So we know that Rn is connected. So we can choose a path gamma from X to Z. And we can, without loss of generality, we can assume that this gamma is transverse to X. Okay, so if this is my X, here's X, little x, and here's Z, I can maybe choose a path like this. And every time it crosses, intersects X, I want it to be transverse. Okay, so we can definitely choose that. And now we can look at the intersection of X with gamma. This is going to be a finite set of points. So X and then P1 and Pk. So let's take the last one. So, you know, we can order this path, you know, we can parameterize the path, and you can take Pk to be the last one. So that means that we can find a path from Pk to Z. So there exists a path from Pk to Z whose interior doesn't intersect X. Okay, so now all that you have to do is now you take a path from X to Pk, and you can do that because X is connected. And now you look at a neighborhood of this path, and you can actually concatenate the path gamma tilde within this little neighborhood to attain then a neighborhood, this chosen neighborhood U of X. So the conclusion is that we can find, a path connecting Z to U minus X. Okay, so this open neighborhood of X without intersecting. Was that clear? I mean, if you want to write down, you know, more stuff, maybe you can write another paragraph. You know, you can write the parameterization of gamma, and you can say, well, at gamma of some T0, you're at Pk, so at gamma of T0 plus epsilon, you're in a neighborhood of Pk, but in that path that goes from there to Z never intersects X, and then you can write down this neighborhood of this path. I mean, you can use the tubular neighborhood theorem too if you want, but you don't actually need it. You just need to take a neighborhood of the path that connects X to Pk, and then you can go along this neighborhood without ever intersecting X. Okay, is that clear? I mean, I hope the picture is enough. If you want, I can write more, but I think if you understand the picture, you can write down the argument. So please ask me if you don't understand the picture. And the point is, U minus X has two connected components. Right, it's just basically, you are in Rn, and you have this box, and you remove this middle. So you have the top, you have the places where xn is greater than 0, and the places where xn is less than 0. So this has two connected components. So that means that that implies that Rn minus x has at most two connected components. I mean, it's an open set, so it's path connected is the same as being connected. So it has at most two path connected components, so two connected components. Okay, so any questions about this first step? No. Are you still there? Yes. Great. All right, so step 2 is that if I can connect Z0 and Z1, if Z0 and Z1 are connected in Rn minus x, then the winding number of x with respect to Z0 is equal to the winding number of x with respect to Z1. And this is mod 2, because I'm not assuming that x is oriented. Okay, so if I have two points that are in the same connected component, then their winding numbers, the winding numbers relative to them are 0. And well, how do you do that? So if you have a path, if let gamma be a path from Z0 to Z1, then you can just write a homotopy h of t x. This is x minus gamma of t over x minus gamma of t. This where h goes from 0, 1 times x to Sn minus 1. So h is now going to be a homotopy between uz0 and uz1. So h is a homotopy from uz0 to uz1. Okay? So that means that the degree of uz0 is equal to the degree uz1. Okay, so because they're homotopic maps. And this, I'm doing this in Z mod 2. So this is the degree mod 2. And this is, it's exactly the same thing. I didn't quite prove it. I didn't quite say it when I was doing the calculation for the degree, I think. But the point is that if you take a regular value, you can take a regular value of uz0, uz1, and such that h is also transverse to a. A regular value of all these guys and a regular value of h. So it can choose a common regular value, and then the pre-image of A is a compact one manifold. And the boundary of this guy is the union of the boundary of uz0 inverse of A with the boundary of this guy. And now we don't have signs because these are not oriented, but the point is that the number of points in the boundary is going to be the sum of the points here with the point here. So the point is that the number of points in here is the number of points in here plus the number of points in here. And this is 0 because you have a compact one manifold, so the number of points on the boundary is even. So that means that these two are the same. So this is mod 2, which implies that the number of points in the pre-image of A is equal to the number of points in the pre-image of UZ1 mod 2. Okay, so it's very similar proof, but it's actually even easier in Z mod 2. Okay, so the degrees are the same, and by definition, these are the winding numbers. So the winding number of X Z0 is equal to the winding number of X Z1 mod 2. Oh, and by the way, I defined the winding number of maps. But as usual, you can always, if you define something for maps and you have a submanifold, you can always, define it for the submanifold using the inclusion map. Okay, that's why here I just put the X. But usually, you'd have the F of the X, so the inclusion of X. So it's just X. Okay, so that's the second step. So now what I would like to say is that I would like to, I would define U1 to be the set of points Z in X in Rn minus X, such that the winding number of X with respect to Z is 1, and U0 will be the set of Z's such that the winding number is 0. Okay? So all I have to show is that these two sets now are non-zero, non-empty. Okay, so because I know the winding number is preserved in the connected component, and I know it has at most 2 connected components. But the step 3 is basically to show that U1 and U0 are non-empty. So I'm going to show something slightly that's going to imply this, which is that if gamma is a line segment from Z0 to Z1 that intersects X at exactly 1 point, then the winding number of X with respect to Z0 is equal to the winding number of X with respect to Z1 plus 1. So, basically, if here's my X, here's Z0, and here's Z1, and I have a line segment that goes from Z0 to Z1, and it intersects X exactly once, then the winding number changes. Okay, so how do we prove that? Well, we can suppose. Well, I'm going to suppose the line segment intersects transversely. So I'm supposing this gamma intersects X transversely. I mean, you can always, find in a neighborhood. It's easy to see that all that you need to show that these are non-empty is to, you look at a neighborhood of a point in X, and you can easily find a transverse line segment from a point on one side to a point on the other side. Which, in principle, you don't know if it's the same side. But locally, at least, it's 2 different sides. Okay, So how do you do this? You just, so because gamma is transverse to x, you can write a vector v, which is z1 minus z0. It's because we are in Rn, so you can do that. So it's going to be this vector v. And since this gamma is transverse to x, we know that the maps uz0 and uz1 are going to be transverse to this vector v over the norm of v. Okay, so now, basically, if you look at, and this is maybe an exercise, but it's simple exercise from this transversality. So now we can just look at the pre-image of this point. So this is a regular value, so you can look at this, and you can look at the pre-image of this. And the point is that if I'm looking at, since I'm doing x minus z 0 over x minus z0, so when I look at the pre-image of this guy, so for z0, this point is not going to be in the pre-image, this intersection point. But for z1, this point is going to be in the pre-image. So the point is that this is going to be the pre-image of uz1 is going to be the pre-image of uz0 with this extra point p. Okay. And kind of clearly, everything else on x, you're going to have the same. If it's in z0, it's going to be in z1 as well, in this direction, and direction given by v. Okay, so then you have one more point in this guy. So the degree of uz1 is equal to the degree of uz0 plus 1. This is mod 2. And this degree is just the winding number. Therefore, the winding number of x z1 equals the winding number of x z0 plus 1. Okay? And that's step 3. Any questions about this? Is it clear why, when you look at the pre-image of these maps, given by, the direction between z0 and z1, you have one extra point in z1 than you have in z0. Okay, well. If nobody says anything, I will assume you all understand. And then the last step is just to conclude the proof. Conclude the proof. So we know that Rn minus x, that u1 and u1 and u0 are both non-empty, because you can easily find points that have the two possible numbers, two possible winding numbers, and so that implies you actually have this disjoint union, and you have at most two connected components. So u1, u0, and u1 are connected. Are connected components. It's actually easy to see by just looking at a neighborhood. Looking at a neighborhood of a point in X, we can see that u0 bar, which is just u0 union X, is a manifold with boundary X, and similarly for U1, similarly for U1. Okay? I mean, this is, even, of course, in higher dimensions too, so I'm not very good at drawing, but I don't know, if you draw some surface like this, then it's going to have an inside and an outside, and both are manifolds with boundary given by the surface. And finally, we have to show that U0 is unbounded and U1 is bounded. So how do you do that? Just take a Z, a point in Rn, such that the norm is very large. So in particular, if you take any norm that's larger than, I think, the supremum of the norm of X. So you just pick Z to be larger than, I think, the maximum of the norm of X, when X is in X. And then you can actually homotope. So then Tx minus Z is greater than the norm of Z minus the norm of X, which is always greater than 0 for every X in X. So this means that the map UZ is homotopic to a constant map. So the degree of this map is 0. Okay, so if you take a point that's really far away, then you can homotope the map X minus Z over norm of X minus Z to the constant map, because this guy is always different from 0. Okay, it's the same that I did before. Okay, so basically that's the end of the proof. Okay, so let's stop here now, and next time we're going to talk about the Borsuk-Ulam theorem, and also I think we're going to also have time to talk about the Poincaré-Hopf theorem. All right.